So in the previous videos, we have discussed how to solve for the zero input response of linear time invariant systems. In the current video, we'll discuss how can we calculate the other part of the total response, the zero state response. Just to refresh our memory very quickly, the zero state response is the response driven by the external input only, assuming all initial conditions are zero. And in the framework of this differential equation based or described LTI systems, that means this guy will be zero. This guy will be zero. And all these derivative terms that you can think of will be zero up to this. Okay. These are the initial conditions we discussed earlier in zero input response. Now, the way to solve zero state response, as I mentioned, will be slightly more complicated. And because it's more complicated, we have to do it step by step. We'll start from a special case. I'll begin with a special case. In this special case is when f of t, the external input, is as simple as a spike or a nudge, right? You just touch or give an impact to the system characterized by delta t, our unit impulse function, at time 0, and see how the system will respond to that. And since this is so special, the output is also given a special name. We call it h of t. So whenever we see h of t, it now carries a special meaning. It is called the unit impulse response of the LTI system. And always keep in mind that the unit impulse response is a special case of the zero state response. And I understand there are a lot of new concepts here already being introduced, but these cases are usually always very important. Knowing each concept can distinguish them clearly will be the first big step and great foundation to do more complex calculations. So how do we solve for that? Now, I will directly give the result without delving into details. And if you're interested in details, the textbook has an appendix part in this chapter that discusses the proof of the following result. Okay. H of t actually can be directly written in the following form. Bn times delta t. I'll first write down this and explain component by component to break it down. Plus PD. And while I'm writing this, try to think about how each one of them can relate to what we have discussed. Times u of t. And that's it. This is the general form of the zero state response when the input is delta t. This is your unit impulse response. Now, you should know when you see this what is delta t, what is u of t. The other three, bn, p of d, y of n of t, may not come to you immediately, but these two things, bn and pd, are something we have already discussed. They both come from the general form differential equation description of LTI systems. I will page up to find that form. So what is Bn? In this equation you will find B's. B0, B1, Bn, and so on. So Bn, n, or this subscript apparently corresponds to the order of your derivative. So Bn corresponds to dnf dt. That's Bn. NPD is right here. It corresponds to the right hand side of your differential equation. How the input function will take in all the differentiation operators, these. Let's come back to this again. Bn is the coefficients of dnf dtn in the differential equation. And n is the order of the highest derivative on the input side, this dny dtn. And in some cases, you may not have this term on the right hand side of your differential equation. If that's the case, that simply means Bn is equal to 0. And in the examples that we have discussed above in this chapter, all of them have Bn equal to 0. And that is because we want the system to be strictly causal. And we'll come to that as well. Okay? But this is what is Bn means. Pd, we have seen that above as well, is this Bn dn plus up to B1 d1 plus B0 and so on. Meaning we need to apply these differentiation operators on the signal that follows it, which is now this yn of t. So the question is, what is yn of t? This is the only term that's not clear to us. What is yn of t? Now, yn of t is, or can be solved as follows. And you will see a very familiar procedure like what you have seen in the zero input response. So that's how it's done. So yn of t will take the following form: b1 e to the lambda 1t plus and so on and so forth up to bn e to the lambda nt. This is exactly how we wrote or expressed the zero input response, and yn happens to take the same form. Of course, here I only illustrate the case where you have distinct roots, but for the other cases it's basically the same. But I use this bi's just to distinguish what we have discussed earlier. To solve for bi's, we use the following special set of initial conditions. I want to say quote unquote initial conditions. Up to d n minus 1 yn dt n minus 1 equal to 1. So in other words, you want to set initial conditions to a bunch of zeros and end the last one with 1. For instance, if n equal to 2, that means y and 0 equals 0, and dy and dt t equal to 0 equal to 1. So it's, you can see slightly different from what you have above, but just you start with zeros and the last initial condition you put will be 1. N equal to 3, for instance, will be the first two being 0. And the last one has 1. That's all. And the rest of the procedures will be exactly the same as what you have seen in zero input response. Okay. And this is the general procedure. In the next video or the next lecture, what we are going to discuss is, we'll use an example to illustrate this process, how to solve for the unit impulse response of an LTI system using this methodology, or using this procedure, or using these equations.